Good afternoon, everybody. Welcome back. We are going to continue talking today about the basics of carbon steel. We spent all our time on Tuesday discussing things that we actually don't see in welding. But the reason we did it is to set the stage to discuss the things that completely relate to welding. But because we're building a really good foundation, and we're building on top of this foundation, things will make a whole lot of sense to you very soon, and that is today. What have we seen on Tuesday? On Tuesday, we saw, we decided that to learn about welding metallurgy at large, starting with steel was a good idea because steel is ubiquitous, and also because steel has some challenges that if we understand those challenges, then we can understand many things in other materials that would be typically simpler. So we looked at iron by itself, and we saw that iron by itself, the atoms in iron arrange in different ways depending on temperature. And I just happened to have this slide here. We said how below 911 degrees C is the atoms arranged in a BCC structure, which we call ferrite, and above 911 degrees, the atoms rearrange into a different way of structure that is called FCC, and we call that arrangement austenite. And then if we go yet higher temperatures in this range here, the atoms arrange themselves yet again on their own as ferrite again, and we call that delta ferrite. And that is in contrast with the alpha ferrite down there. But truly, it's the same thing. It's the same arrangement of the same atoms. It's just that one happens at very high temperatures and tends to have some properties, and the other happens at very low temperatures. Then we said, given that we understand how iron behaves with temperature, let's see what happens if we add carbon. And this matters because that's the definition of steel, iron and carbon. Right? And then a little bit of lots of other things, but iron and carbon, that's steel already. And so if we add carbon, interesting things happen. For example, austenite now is stable at lower temperatures, below 911 degrees. So here we have the blue line marks the composition of a 0.4% carbon steel. That would be something like a 1040, IC 1040 steel. And what we see is that in this case, we have the austenite is stable even down to 800 degrees. And also, austenite is stable above the 1400 degrees, even to 1500 degrees. So carbon is what is called an austenite stabilizer. We also saw a number of other things, that there's so much carbon we can put in iron, and if it is with the atomic arrangement of austenite, then we can put up to 2.1% carbon in the austenite. That's a lot. Now, if we have, I say a lot because 0.4% is already a lot of carbon from the point of view of welding. 2%, imagine that, is 5 times that. Now, ferrite, when the atoms arrange themselves in the crystalline lattice of BCC and is ferrite, it can take very, very, very little carbon. It's 0.035%, give or take. Right? It's so much less, right? It's like, what is that? 500 times less carbon. So we got to see that. And we saw that when the carbon is in excess, it doesn't precipitate as graphite flakes. It doesn't precipitate as chunks of coal, right? Graphite precipitates in the case of cast irons, but we're not going to be worrying about that right now. We're going to be worrying about steels. And in steels, the way it precipitates is in the form of this kind of a ceramic or some sort of intermetallic. It's Fe3C, cementite, right? It's a very complex compound, right? And it's hard and brittle. And then we saw in the iron-carbon phase diagram, we have these single phase regions where, for example, this marked as gamma says this is all iron with carbon in solution. We have this little triangle here that in reality continues down within the thickness of the line, and that is iron with some amount of carbon in solution. There is pretty much no carbon in solution, almost none, and that is ferrite. That's a single phase. Cementite is like line compound. This is a stoichiometric compound, and lives in this line. And then in between the single phase fields, we have the two phase fields. None of this is new. All of these are things that those of you with an undergrad at U of A have seen in MatE 202, right? And those who come from other universities have seen this in your introduction to material science. And the two phase fields are this one here where we have austenite and cementite. But the really interesting for us, there are two. One is this little triangle here that looks like the sail of a sailboat. Here we have both ferrite and austenite coexisting. This is what is called the intercritical region. And many important things happen, and this part here helps us understand important aspects of the heat-affected zone, which we will discuss either at the end of today or on Tuesday. And the other region of interest is all this big square, which really is not a square. You see that it has this kind of little corner shape, or it's not a rectangle, right? But in all this rectangular-like area, we have two phases coexisting, that is ferrite with cementite, right? How much ferrite and how much cementite, we use the lever rule for that, which I'm not going to get into, but it's something that in every introduction to materials you see. And this structure, there is a mixture of, before I get there, and if I'm on this line indicating an alloy, when I reach this point, there is the eutectoid temperature, I know I have ferrite of this composition where the red point is indicating, and I know I have austenite if I'm cooling just before I cross the line at that composition. When I cross the line to below the line, now I'm going to still have ferrite at essentially the same composition. Everything's happy. And I'm going to have now the austenite transformed into a mixture of ferrite and cementite, which we call perlite, right? And it looks like a fingerprint. We discussed this. You have seen this in introduction to materials class. When we are in a composition such as this one of 0.4% carbon, as we cool down, the first thing that is going to precipitate is ferrite. And because it's the first thing that precipitates, we call it primary ferrite. That is in contrast with the other ferrite that is going to precipitate when we cross the eutectic temperature. Because in that case, when the austenite turns into perlite, there is some amount of ferrite, right? But that's not primary ferrite. Nobody calls it secondary ferrite, right? But it's definitely not the primary ferrite. It's a ferrite that is part of the perlite. And perlite is not a phase, it's a microstructure. Although fine ferrite looks all of the same color in an optical microscope, and sometimes you feel tempted to say, oh yeah, all this is a single phase. It's not, it's two phases that are closely intertwined. So we talked about the effect of temperature. We talked about the effect of carbon. And then we talked about the effect of time. Let's see if I have something about time here. We talked about the effect of time. And in the effect of time, let's see. we said how in these experiments that people have done for real, and they have nothing to do with welding. You have something hot that was pure austenite, and then you quench it, but not to room temperature. You quench it to something that is still red hot, but you went very quickly from austenite to red hot, and typically nothing will happen if you don't cross any of the transformation lines. But if you cross them, you're going to have a transformation that starts slowly, then progresses fast, and then goes slow again. And this transformation that really starts happening immediately and really never finished, you don't measure that. You have to wait some time until you see something happening, right? And depending on when you see something happening or what theoretical calculation you're doing, you define arbitrarily, but in a way that most people tend to agree, you define a start point. And is this the point at which you start seeing things? And you define a finish point. That is the point at which you don't see a change anymore. So you don't worry about the abstract concept of asymptotics of mathematics. If you see something started to happen, you call it a start. If you see nothing happens later, you call it a finish. With the agreement that there is some arbitrariness in that definition, because different equipment can see things with different accuracy and can give you different results. Now, based on this start and end, we could make diagrams such as these, which we call TTT, time and temperature transformations, right? Diagrams. And we plot for each temperature what the start time is and what the end time is. And is pretty cool, because now for a given alloy, one given alloy, one given starting austenite microstructure, right? So austenite has grains. If the grain is bigger or smaller, it's going to make a difference. But let's not worry too much about that right this moment. We would say, at each temperature, we have one start of it transformation and one end of the transformation. We talked about how at high temperatures, the transformations result in coarse microstructures, and how at low temperatures, the transformations result in finer microstructures. We also talked about going too quick. We don't give we also said that what determines the time to transform is the ability of the carbon to diffuse out as the ferrite is generated, because ferrite can take very little carbon. And that is what sets the time. The time for transformations of that type are set by this diffusion of carbon in this type of diagrams, in this type of steels. But if I quench too fast, I don't give it time for the carbon to get out, then the carbon stays trapped, and the austenite, instead of transforming directly into ferrite, transforms into something that resembles ferrite, but instead of being a cube, now it's like a box. So instead of being a BCC, body center cubic, it's a body center tetragonal. And this is very hard and brittle. And then what we saw is that if we don't cross the martensite line, but we do a transformation at low temperatures that is not martensitic, we get this hybrid that is kind of martensitic and kind of pyrolytic, that has some amount of diffusion and some amount of transformation without diffusion, and which we call bainitic transformation. It's a hybrid transformation, and some people would say the product of transformation is bainite, but there's so many different names for the product of this bainitic transformation. I'm not going to worry about what we call the end product, and we're going to discuss the many type of end products of this bainitic transformation today. So we know so much. We know effect of temperature, effect of carbon, effect of time. And then what we started at the very end of the class on Tuesday, and is what I want to pick up today, is okay, how about the effect of alloying? As I mentioned to you, the time constant for the transformation was given by the diffusion of carbon. But if I put alloying elements, two things happen. Number one, some alloying elements might need to diffuse too. And if the alloying elements need to diffuse, they might diffuse much lower than carbon. Carbon is a very small atom that lives like somewhere inside the iron lattice. And the iron lattice is full of holes. So it can go anywhere it wants. Now, if instead I have a substitutional element that could be manganese or nickel or things like those don't go through the lattice. They need to wait until there's a hole in the lattice to go and substitute the iron in that other hole they found. The bottom line is that these bigger atoms, these metallic atoms, these substitutional atoms, diffuse a lot slower. And what is the consequence? They make our transformation slower. In addition, some of these elements also stabilize the austenite, or the opposite. It can stabilize the ferrite. But now we can start playing games through the thermodynamics, saying, okay, is my austenite more or less stable? If you remember, if we're too close to the stability region of the austenite at high temperatures, our transformations are very slow, even if diffusivity is high. And the reason the transformations are slow is because what we call the driving force, like this amount that we're out of equilibrium, is not so big, right? So if we need to move a very small weight, we might think we do it fast. But if we're not very strong, it might not be so fast, right? So that's what's happening. So alloying elements have these two functions, they play these two roles. Slow down diffusivity, to play a slow role in diffusivity, and also change the stability of phases. Typically, the more alloying elements you have, the slower the transformation is. If the transformation is slow, that means that a given cooling rate, instead of like starting to find my primary ferrite and my perlite or bainite, whatever it is, I might keep going, and never find these new transformations because I didn't give them time to happen. And guess what? We end up in martensite. For people doing heat treatment, this is awesome, because if you wanted to do, for example, a very, very big shaft that you wanted to temper, to do some sort of a quench, the inside of the shaft, doesn't matter, you can quench it at 0 Kelvin on the outside, and the laws of heat transfer, which many of you took with me, the laws of heat transfer say that even if the surface is at 0 Kelvin, the core takes a long time to diffuse the heat away, to take the heat away. I'm not talking about mass diffusion, I'm talking about diffusion of heat, of which we have a whole course, right? So how do you fix that? You cannot fix heat transfer, but you can fix the metallurgy. So higher alloying elements give you the ability to quench big components that cool down slowly. That's awesome for heat treaters. Now go and weld those. The transformations are so slow that we end up most of the time with martensite. So let's see. Well, in this slide I have here, what I'm showing is some elements. They say austenite formers. And I don't worry about the numerical values here. But what this slide is showing is how some elements stabilize the austenite. Remember when I showed in the iron carbon diagram how a little bit of carbon made the austenite a lot able to exist at lower temperatures and also at higher temperatures, in which should have transformed. But carbon makes it stay stable. And it's a very powerful austenite stabilizer. The vertical axis here is talking about the enthalpy of transformation. Let's not worry about that. This is thermodynamics, but this just shows how much what a stabilizing effect it has, measured in a metric of thermodynamics. What else is very stabilizing of austenite? Nitrogen. And nitrogen is also an interstitial element. For those of you who might have heard about duplex stainless steels, nitrogen plays a role because in a duplex stainless steel, we have both ferrite and austenite. And if we have more nitrogen, then we are having more austenite, right? And it's a way to play games in the final microstructure of these steels. People have even tried welding those with a shielding gas that has nitrogen, trying to stabilize the austenite. Very interesting. Other stabilizing elements for the austenite, we have manganese, nickel. Nickel is another FCC element. You could say that nickel is pure austenite, right? Copper and nickel are more or less the same thing, right? They are fully miscible. Also stabilize austenite, zinc too. And what stabilizes ferrite, which is the opposite, the opposite result? Oops. We have, they put zirconium here, that is a lot, but we don't use much. Typically, zirconium gets trapped in oxides or carbides. We have titanium, tin, some impurities such as phosphorus, vanadium. Most of these are very strong carbide formers. All I'm trying to show you here is that when you start playing with alloying elements, you change your hardenability very much. And in showing you this, I'm showing you how some of these change the one aspect of hardenability, that is the thermodynamic aspect. So let's take a look at these curves, which I chose on purpose. The steel on the left is a steel we have already discussed. This is our 1040 steel. It's a relatively high carbon steel. This is at the limit of what we would weld happily, right, in being a carbon steel. Right? And what we see here, we see that if we do our very artificial heat treatment of doing a quench and holding at a temperature, we would get as a primary ferrite. We hold it and eventually turns it into perlite. And if we do this hold at lower temperatures, we go straight from austenite into the final product, that is bainite. It's something I want everybody to be on top. These TTT diagrams and the ones, more important ones that we're going to be using, called the CCT diagrams, they all use different names for the same thing. Some people would put here a P for perlite and a B for bainite. It's true. Some people put F plus C, which means ferrite plus carbides. And guess what? It's just as true. I don't know why they haven't agreed on naming things all the same way. But you have to know, when you look at a diagram, what you're looking for, even if it says P or B or F or C or is in German. As a matter of fact, we have lots of German diagrams Alejandro was showing on Tuesday. You do not need too many labels to know what's going on. Primary ferrite, perlite. Here on the left, we have austenite, and here the austenite starts to transform. Look at what happens if, in addition to the carbon and the little manganese we have now chromium, moly, nickel. Like this is, now we got like into a really spicy meal, right? Like we put all kind of condiments. And now, for a 1040 steel, right here, we would have started a transformation in less than 1 second. Less than 1 second to start a transformation. Look at this. Now, we don't start transformation before than 10 seconds. Let's think about this. If in a weld, I cool down in any more than a second, I'm going to have in a 1040 steel, let's pick 5 seconds. If I cool down in 5 seconds, I know I'm going to have some amount of primary ferrite and some amount of ferrite and carbide, whether it's perlite or bainite. We'll discuss this later. However, if I take 5 seconds to cool down this steel that is so highly alloyed, see what happens. We will end up straight in martensite, right? Very hard now. This is easy to weld. This is very difficult to weld. That's the effect of alloying. Here we get to see also the primary ferrite region, same as we have here. We get to see here this F plus C, which, what do we call this microstructure up here? Anybody wants to type something in the chat? What would it be, the microstructure that belongs at this transformation part here? Yes, it's perlite. How about down here? What is the microstructure we would expect? Bainite, exactly, right? So we start to understand steel is alive. Steel is alive, and not only is alive, it's our friend. We can do so many things with steel. You want hard, you want malleable, you want strong, you want tough. You tell me what you want. We can make it happen with steel. And in welding, the challenge is that whatever we wanted to happen has to happen based on the weld, on the heat cycle of the weld we made. That's why we're taking this class. And that's why we're trying to understand everything together. So now I want to talk about welding, because everything I told you so far, none of that applies to welding, except all the fundamental concepts are the same, right? So we talked about effect of temperature, effect of carbon, effect of time, effect of alloying elements. All those are gonna be the same. But when we talked before about like this very artificial heat treatment of I austenize at 800 degrees for 1 hour, then I cool down on a salt bath and hold in the salt bath. You never do that. What do? You heat something up and you let it cool down. Now, in this case, if we go into this diagram, see the horizontal axis was time, and the vertical axis is temperature, and here is cooling, right? We used to say we hold it at a temperature, but in reality, for welding and most other heat treatments, you cool down in a ramp. I have a question here. Can anybody tell me why, if I'm saying, well, I haven't said it yet, but I'm going to say it now. I'm going to cool down at a constant cooling rate, so many degrees per second. So I would like somebody to tell me if my cooling rate is constant, why the curve is bent like a banana here. Yeah, thank you. Because it's log scale, right? So this is constant cooling rate, but because the vertical axis is in a linear scale and the horizontal is in log scale, then it turns like that. Log scale curves are so powerful, but they need a lot of our attention. In this little, if I have up to here 1 second and up to here I have 10 seconds, in the same space, that I went from 1 to 10, now I went from 10 to 100. The time here starts to flow very slowly, and time here is, on the left, is moving very fast. All right, so this same diagram in which we have spent so much time, and it's not good for welding, in one step, in this one slide, I'm gonna transform it into the diagram that matters for welding. The reason I have not done this before is because the microstructures that come out of this, the real welding diagram, is a combination of all the microstructures we have discussed. and it makes it very difficult to explain. When people first started to study phase transformations in steel, they were doing like continuous cooling experiments, and they would see this zoo of microstructures that they couldn't make much sense. Only when they started to do these very artificial heat treatments of going to a certain temperature and holding and seeing the transformation, these people call them isothermal heat treatments, they start to say, aha, now I see this one microstructure and I understand this. So we're going backwards. Instead of starting where everybody started, in which they were confused, we're starting from what people understood, and now we get into the complex. So these two diagrams in the left and in the right correspond to the same steel. That's why I've been using this steel. And what do we see? Number one, vertical axis is the temperature in both. Number two, horizontal axis is time in log scale in both. Number three, on the left, we have austenite. And here we have austenite. Number five, I forgot what number it is. Now, another similarity. We have lines that indicate start and end of transformation. In this diagram, we talk them to death. Here, we have the same. Start of transformation is one line. Start of the other transformation, finish of transformation. Other similarity, the faces that appear are the same. Look, above the transformation temperature, we have nothing happens. Above the transformation temperature, nothing happens because there's no driving force, right? If I'm too hot, it wants to be austenite. And this says nothing is going to happen. The TTT curve on the left and the CCT curve on the right says nothing's going to happen. Okay, we're fine. And then when something happens, we had primary ferrite, right? Here we have a primary ferrite. It says A plus F, means the austenite we have in the left starts to transform into ferrite. This is first ferrite that appears is a primary ferrite. And guess what? Here they use other words that are not meant to confuse you, although they're quite successful at confusing people. They put A plus F here. Fine, but I know what it is. Here they put only F, but I know that this means above this line, I have only austenite. On the right of the line, I start to have primary ferrite that is started to appear. Look, here it says F plus C being not very committed to whether it's perlite or bainite. And here they tell me, aha, P, perlite. Perlite starts to appear. And I want to emphasize this again, whether it says A or B or F or P or whatever it says, or it's in German, you must know what's going on. You must know what's going on. And here we have a perlite, but look at this. Here it talks about bainite, right? Here it starts to talk about like how it forms bainite, right? And very interestingly, because from the point of view of these people doing these diagrams, they call it bainite. At the end of today, I'm going to show you that what they call bainite can be a whole zoo of very different things, right? And guess what, too? You can get also martensite. You see this horizontal line? That is a transformation into martensite. So left diagram and right diagram are kind of the same, but they're not exactly the same because this one on the left is made for the very artificial isothermal heat treatments. And they are read left to right. You read this diagram on the left, like saying, if I hold at 1200 degrees, things happen as I move from left to right. But the diagram on the right, it reads following these lines that are marked. That are the lines of continuous cooling. So we have many, many lines. The lines on the left correspond to very fast cooling. The lines on the right correspond to very slow cooling, and typically it's cooling from a high temperature into austenite. And sometimes is for for example, could be 800 degrees for normal, for heat treatment diagrams. For welding, they use, I believe, 950 degrees to have big austenite grain sizes and represent the effect of that coarsening can have. And so how we read these diagrams? For example, let's see if I have something. No, how we read this? Let's see. Let me see. Okay. Before I read the diagram, I have here a summary of these two curves, right? And there are similarities, and I list them here. I want to bring something up. Each alloy needs one different diagram. So if you have a diagram, it's only good for that alloy. In addition, if you have different austenite grain sizes to start, the diagram shifts. So in addition of saying this diagram is good for this alloy, they have to tell you this diagram is good for this alloy and for this prior austenite grain size, or for this austenite holding temperature. There is an indirect way of saying grain size, because if the holding temperature is high, the grain size is big, right? So the effect of grain size, austenite grain size, is much smaller than the effect of alloy, but it matters. Okay. Something else about these diagrams. These diagrams tend to be quite generous. For example, if you follow this red line here, it says that if you cool to, in this case, says 550 Fahrenheit per minute, you gotta love those units, right? But you're going to end up with a Vickers hardness of 215, right? Or if you cool down faster, you end up with a 284 Vickers, right? Or if you want, they have a conversion too for Rockwell. They say so much. And in the next slide, I want to tell you a little bit more. So I'm going to work through this example, but if you look at all the exams, you see that I ask every year a question like this. Give you a CCT, and I said, tell me for this cooling rate, what we should expect. Right here we have 4,100 degrees per minute. This is a perfectly possible cooling rate in welding. And this diagram speaks. These diagrams are amazing. These diagrams are like a map. Like you go to a place you have never seen. If you have a map, you can navigate a new city. And with this map, this CCT map, you can say so many things. So if you have a weld that has this cooling rate, my question is, what is the final microstructure of that weld? And what is the hardness of that weld? So let's do this together. Okay. Before I... So this is the cooling rate that matters, and it's marked here, 4,100. So we start cooling down here. I'm not gonna worry about this little hump here, but if I don't say anything within a few minutes, somebody asks me, because I have something cool to say about these humps. But if I'm at this point where the red dot is, I would like somebody to tell me what the microstructure is at that point in time and temperature. What phases do I have? Pure austenite, thank you. We're 100% on the same page. If I cross this line, what happens as I cross that line? Yes, primary ferrite. Primary ferrite starts to come out. Something interesting on this diagram. how much primary ferrite do I have by the time I start to cross the next line? 8%, right? This diagram is very generous. It's saying that, okay, I'm going to have, by the time I start to have the next transformation, I have 8% primary ferrite. Now I cross it. What happened when I started to cross it? What phases do I have now? Phases, I said phases. What phases do I know if I just cross that line? Yes, yes, yes. We have, no, missing one. You're missing one here. So the answer I got is almost true. Yes, an austenite. So I have austenite. Austenite is the gasoline in my car. As long as I have austenite, I'm transforming. So until I finish transforming, I always have some amount of austenite. At this level of simple alloys we're discussing, right? So we have austenite, only austenite at the beginning, then austenite and primary ferrite. Now, austenite and primary ferrite and carbides, right? This cementite. Now that we discussed what phases we have, I want to know what microstructures I'm going to see. What type of microstructures would I see at this point that is marked in the diagram? Yes, you have an untransformed austenite that will transform very soon. You start to see perlite, and you start to see perlite, right? And perlite is a mixture of this ferrite and carbides. And what else do I see? What else do I have there? Yes, you have ferrite. And the ferrite you have, so if we say we have ferrite and perlite, that means we are not we're talking about primary ferrite and perlite, right? We're not putting the ferrite of the perlite in our accounting. And how much ferrite? I want a number. No, 8%. This is how much primary ferrite we had. Somebody suggests 9, but no. So these diagrams make a number of hypotheses, some of which are not really true, but let's take the lie and move on, right? The guy says 8% primary ferrite. The truth is sometimes the primary ferrite keeps transforming too, but let's not worry about that. Let's say that it gets locked at 8%. Any new ferrite is going to come from the perlite, and it's not primary ferrite anymore and looks so different. So at this stage, at this point here, we have a bunch of untransformed. What do we have? We have, let's say, 91% austenite that has not transformed. 91%. 8% primary ferrite, and let's say 1% perlite. All right, keep going down. What do I get now? What is my microstructure right here, just before crossing the line? What do I have there? Yes, but I want to, what we had before was 8% primary ferrite some bunch of untransformed austenite. We had some perlite. I want to know how much perlite. Yes, yes, thank you. And 7% austenite. So can I keep transforming? Of course, yes. I have 7% of fuel in my tank. 7% fuel. All right. So I'm gonna keep transforming. What am I getting there? What as I crossed the line, and what started to happen? No, perlite is done. Perlite is done. Following this diagram, which is not exactly true, but I'm not going to worry about subtleties. Yes, bainite. So we froze 8% of primary ferrite. We froze 85% of perlite. And now, oh, bainite starts to appear. But if you remember in our previous diagrams, you got either fine perlite or coarse perlite or bainite, but you didn't get all of them. That's why doing this type of experiments was a nightmare, right? Welding microstructures are very difficult, right? And that's why I wanted to explain the easy ones first, however artificial, because now we are seeing a little bit of everything. Okay, so we started to see bainite. Isn't it cool that we get to see bainite appearing at lower temperatures? We saw it from the previous diagram that we started with coarse perlite, finer perlite, bainite, right? All right, I'm at this point here. And I'm at this point, I just crossed the line. Sorry, I'm at this point just before crossing the line, right? And what do I have just before crossing that line? No. Before crossing the line. No. we have, okay, we have frozen primary ferrite, 8%. Aha, 6% bainite. Here's the B. But if they didn't give us the B, we must know it. If they put it in German, we must know it. Because that's all we have in these diagrams. Right? And there's no diagram in which the things are flipped. The way they appear is in this sequence. All right, so now we have 8% ferrite, primary ferrite frozen in place. We have 85% perlite frozen in place. We have 6% bainite frozen in place. Am I done? Ha ha, 1% fuel left. Yes, what do I do with that fuel? I cruise, and actually up to here is all the same. And now, these guys, this 10% is for the left one. If I am here, I still have the same. So this line here is a line of nothing happens. Bainite stopped transforming, but I kept 1% of fuel. It's like credit card at the end of the month. You have 1%. You cruise. And then you cross, end of the month. Guess what? You use your last 1% here to do, what is the 1% used for? Martensite, right? So isn't this awesome? At this cooling rate, in a single experiment, we got to see everything we had discussed before. This is real. Actually, this diagram doesn't come from theory. People did it, right? And these microstructures are very difficult to interpret when you look at them. I wanted to tell you about this little hump, and it's very interesting. So when you're cooling down, you take heat out, things cool down. But now there's something funny. When the austenite here start to transform into perlite, right? We have a phase transformation, and for those of you taking thermo now, this is all about the enthalpy of the transformation, right? Like you have at the point of equilibrium, the free energy is the same, but the enthalpies are very different between austenite and perlite. And when they transform, the consequence is that the enthalpy is very high. And this enthalpy, that is thermal energy, in our heat transfer class, we talk plenty about enthalpy. This thermal energy gets released. And isn't this amazing? When it gets released, it reheats the sample. You were cooling the sample, but the sample is going up in temperature. That's quite paradoxical. And what happens is you start to take heat out of the sample, and the sample comes down in temperature until there is a transformation and all that heat gets released. This is called recalescence. And it's such an amazingly cool thing to see. We had one of the guys in the lab do a whole PhD in measuring this recalescence. And from the recalescence, you can reconstruct the phase transformations. So although it looks like just a bump and an annoyance in these diagrams, there is so much information here. We will not worry about this, but I want to tell you, for example, something we have not done yet, but I want to do in the lab. We can measure this recalescence during the cooling of a weld, and we have a $150,000 thermal camera to do that. And if we do that, we can talk about phase transformations live. Okay. Why does this effect not occur? Okay, when you have a transformation, these transformations have an amount of enthalpy associated with them. So if the transformation either very little transforms or the transformation involves a low enthalpy, you don't see that much of a change. In the biggest change and the biggest jump we see here is for two reasons. One is we're transforming a lot of austenite into perlite. But number two, transforming austenite to ferrite is more or less the same thing, right? It's the same atoms rearranged. But transforming austenite into cementite, in which you go from the metallic bonds to the covalent bonds or whatever bonds are in cementite, are very different, and they involve a lot of enthalpy. That's why we see this big jump here, but the jump here is not picked up by the instrument. Really cool, really cool. Okay, here you have the numbers, right? And if you ask me what is the final hardness, I can tell that to you too. And guess what? I just gave you many thousands of dollars worth of information just because I had this figure. And if you don't have this figure, making this map is going to cost you many, many thousands of dollars. And we'll be very glad to take your money because we have the machine to do it in our lab. We're going to make this and much better. And one of the world experts on this is your TA, Alejandro. So if you find this interesting and exciting, he can show you someday when we open the lab, our machine, and he can talk to the end of eternity about this because there's so much to say. Now, having 287 hardness can be too hard. Having martensite can be too hard, right? So look at this curve. It says that if I were to have a slower cooling, I have softer microstructures, and I would have microstructures that have no martensite, right? Look, 10 and 90, done, no martensite. If I cool really, really slow, I get really, really soft. Conversely, if I cool very fast, I might end up with 10% martensite. That's not your happiest weld, right? And now we start talking very interesting things because we know our steel. We can start saying, aha, I want a slower cooling. Well, we can change the heat input, which we have discussed intuitively, but you guys are going to have a lot of formulas to calculate the cooling rate for a given heat input. We can use preheat. Preheat is going to slow down the cooling, and all these formulas will give you are formulas that include the effect of the preheat. Or you can do post-weld heat treatment. That is a lot more complex because that means, all right, I'm going to suck it up that I end up with a bunch of martensite in my weld. I'm going to do a heat treatment and temper this martensite. Very different ball game, right? Now this type of heat treatment would be more of a traditional heat treatment, putting things in an oven. That said, some things are more difficult to put in an oven. If you don't like your welding a ship, it's going to be tough to do a post-weld heat treatment there. All right. I want to tell you about a few other effects that are involved in welding. One is the effect of nucleation. So if we have to have a transformation, you have to start somewhere, right? There's whole theories about that, but if you take my words intuitively too, things don't transform until they found a place where to start. If you give them lots of places where to start, then the transformation starts soon. And if the transformation starts soon, that means your chances of a soft microstructure are higher. If you have few nucleation places, you have few places where to start the transformation starts late, and your chances of ending up with martensite or hard bainite are high, right? So nucleation sites matter. For example, the grain boundaries are a place of nucleation. And if your austenite grains are very big, that means you have a lot of volume with little area in which it can nucleate. So big austenite grains are more hardenable than small austenite grains. Big austenite grains are more or less the same as having higher alloying elements. You can have inclusions for the nucleation. And one funny aspect of welding is that in places such as the welded metal, you want to have inclusions. Now, you want to have the inclusions that are appropriate, are not going to destroy your toughness. And for example, inclusions of titanium oxide, small amounts. Most people believe that they nucleate ferrite at this interface between the austenite, the original austenite, and the titanium oxide, right? And this is so much so that welding consumables often have titanium to create this titanium oxide that nucleates this ferrite. And if you use, remember we talked about manganese and silicon or ways of taking oxygen out of your weld. Now, if you take all your oxygen out of your weld, you don't form this titanium oxide and you don't nucleate this ferrite that is so beneficial. And you may end up with a weld that has a pretty poor microstructure and pretty poor properties. Isn't this interesting? Typically, you don't like oxygen. But zero oxygen in welding is not your friend either. Not in steels. So let me show you, this is a classic schematic. These hexagons represent the primary austenite grains, right? So the hexagons in steel metallurgy are the primary hexagonal grains, the primary austenite grains. They are not hexagonal, to be clear, right? But they're more or less equiaxed. So people put a hexagon. It's not that far off. It's more or less equiaxed. Now, when the transformation starts, what we have is this thing that happens around it that is the primary ferrite. Primary ferrite appears around the grain boundaries in austenite. Now, if I cool slowly, I have lots of primary ferrite appear. If I cool fast, I have less time for nucleating this primary ferrite, and that's why, see the T85, this is a long T85, medium T85, and if the T85 is very small and we cool down very fast, we don't even give a chance for primary ferrite to appear, right? Now, as time goes by, ferrite growth And this growth is called Widmanstatten ferrite. It's a very coarse ferrite phase, right? And has these big kind of fingers or laths that grow in. This is Widmanstatten ferrite. And we can have a little bit of that also if we cool down faster, not all that much. Now, the triple points in the grades, these corners in the hexagon actually represent points in which we have three grain boundaries meeting. The grain boundary of this grain against the one that would be here, and against the other one, the grain that would be here. Here they didn't draw a line, but there is another grain boundary. So those triple points, we can have some primary ferrite appearing at those would be the most powerful nucleation sites. As we keep cooling down and the temperatures are lower, ferrite keeps growing, and then some of the ferrite grows inside this austenite that is still untransformed. Because the transformation is at low temperatures, this type of this ferrite that appears here is a ferrite that appears from a bainitic type of transformation. And so it's a mixture of what is called a displacive transformation that involves no diffusion with a little bit of carbide precipitation that does involve diffusion. So if we cool down faster, then we have quite a bit of these structures here this ferrite that nucleates inside through bainitic processes. And if we cool down really fast, right, we have these very much finer bainitic plates, this much finer bainitic structure. And actually, they didn't put it here, but if you go too fast, it's all martensite, right? Now, I was talking about effect of cooling rate, but time and alloying is more or less kind of the same thing. Like if I cool down faster, is more or less equivalent of putting more alloying elements, because either I cool down faster or I transform slower. So these two are more or less the same. Oxygen content relates to what I was mentioning about having nucleation sites. These little worms that are nucleating here, these worms here, those are the worms that nucleate at these nucleation sites, for example, titanium oxide. And what we have here is about austenite grain size that, as we discussed before, has very much a similar effect to alloying additions. That means, in this case, the big grain size, we have a lot of volume with little surface on which to nucleate what will transform. So I want to, in this, now this is a CCT diagram. I don't need to tell that to you. You should recognize it. And we have what is shaded, we see on the left, austenite, ferrite, perlite, bainite, and we have two diagrams. And what is the reason? Is one, the one on the dashed lines is what you would do with a 1,000 degrees austenite hold, and has one given austenite grain size. The other one that is shaded is more representative of welding, that corresponds to 14 to much higher holding temperature, in which the grain size of the austenite grew very coarse, and because the austenite is coarser, everything slows down to slower times. So same material, but two different initial austenite grain sizes, and they have very different hardenability. Okay, I will go quickly over a sample transformation if we were to have different cooling rates and what the microstructure looks like. I'm going to be using the curves, the dash curves, not the full curves, right? And just because that's what I have that would match the best. So in this case, right, if we cool down very, very slowly and say it T85 of more or less 100 seconds, which we have here, this is a microstructure we would see. These big blocks are the primary ferrite that appeared at the grain boundary of the austenite. And inside it, we're going to see, I'm talking about the dashed lines, right? So we get to see some primary ferrite, then some amount of perlite, that is what is dark. If it is big enough, that is perlite. If it is very small, you don't know if it is just a grain boundary. But when it's big, that in this alloy, you could say is perlite. And then you have some amount of bainite. That are some phases that are a mixture of the black and the white. But you get to see primary ferrite, perlite, a little bit of bainite. If I cool down a little bit faster, I don't get to see perlite anymore. I'm talking about the dashed lines again. If I cool down faster, say a T85 of 10 seconds, I don't see perlite anymore, right? And I go straight from pure austenite to primary ferrite to bainite. And look, this is the primary ferrite. You see that they're big and kind of long. They are marking the grain boundary of the prior austenite grain size, the prior austenite grain. So you see clearly there is nothing hexagonal here. But let's compare this slide here, this ferrite in the grain boundary. This is the ferrite they are talking about, this ferrite around here. And you see this Widmanstätten ferrite? You see this Widmanstätten ferrite there? You see it here, how it grows, right? And what grows in between the Widmanstätten ferrite is some carbides that are precipitated, right? And then all this other kind of jumble, whatever we call it, this is a bainitic microstructure, a microstructure that comes from bainitic transformations. So primary ferrite, including some Widmanstätten ferrite, and then this bainitic microstructure inside. If I cool faster, in this case, actually, I don't like it so much, but okay. If we cool down faster, we get to see that we have less primary ferrite. In this microstructure, we don't even see the primary ferrite. And we start to see a mixture of ferrite, which is the white, and the black, that is the carbides. And they can be aligned or non-aligned. We'll discuss that later, right? But we see this mixture of primary ferrite, of ferrite, not primary, of ferrite with the carbides. And this microstructure comes all from a bainitic transformation. And this is all, I see no primary ferrite in this case. In this other case, at this T85, we went from 100 seconds to 1.6 seconds. This is kind of laser welding. And what do we get to see? In this case, we get to see the same bainitic microstructure, which is much finer. And it makes sense because faster cooling is the equivalent of lower temperatures. With faster cooling, we end up with finer microstructures, right? And we see this combination of ferrite and faces aligned. In this case, you can trace some amount of primary ferrite. This is primary ferrite. And I know because look at how big and elongated they are, and they have a shape of a grain boundary. I want to tell you something. If you tell me, are you betting your life that this is what it is? I would not. And no metallurgist would do it because it's nearly impossible to see this exactly how it nucleated. It's just, if it looks like something, we call it that something. If you say, are you sure? We're never sure. Now, no, I'm a mechanical engineer. I'm talking about the real metallurgist, right? So, and the way I'm going to ask you questions and the way we're going to grade things is if you recognize, if something looks like something and I ask you to name it, you name it as what it looks like. Look, here we have another long grain here that is likely to be marking an austenite, prior austenite grain boundary. Question. One question is if we have lower temperature but faster, lower temperature, okay, doing a cooling, you go from high temperatures to low temperatures. So by the time you finish, you have everything from high to low. And if you go fast, your chances of martensite are much higher, which I'm going to show you. Now, look at this. This is if you cool very, very fast, and you have this small amount of ferrite, right, of bainitic structure, of ferrite in bainitic structures. But all the rest is martensite. All this rest gray thing, this is martensite because we cool down very fast. So fast cooling can end up in martensite, right? Look at how different this microstructure is from the previous ones, but it's the same material, always the same material. And if we cool down even faster, there's no traces of these bainitic structures. There's no ferrite now. There's no ferrite and carbide. This is all martensite. Isn't it completely different from the other ones, right? And of course, if you want to characterize deeper and deeper, there's no limit to how many $1 million equipment you might need to characterize. But from the look, we can say many things and typically be right. And for sure, if you look at this microstructure and compare it with this, it's the same material. I can tell a very big difference between that or this. These two look similar, or this one, which we have some bainitic microstructures here at the austenite grain boundaries, and this one in which we have nothing. So we'll discuss more about microstructures on Tuesday, but going back about like the behavior of steels to welding, that now we're talking about welding, right? Using the same concepts as before. People tried, and this is something Alejandro mentioned on Tuesday, people tried to capture the effect of alloying elements in the steel. And they tried something that has nothing fundamental. They said, if we try this, does it work? And they came up with the concept of carbon equivalent. That is something very simple mathematically, horrible from the point of view of fundamentals, extremely practical. Because although there's no fundamentals behind these numbers here, they tend to take us to the right places. What is this concept of carbon equivalent? If you remember, we said, if I add alloying elements, I'm going to move my curves move to the right because it becomes slower. And this is also true for steels with different amount of carbon. So they say, I know the effect of carbon in the plainest of all steels. I know it. But if I were to put a little bit of silicon in addition to the carbon, to what carbon steel does it resemble? And there you go. Say you put 5.5% of, no, that's it, ridiculous. Okay, and for the sake of example, 5.5% silicon in your iron and nothing else in your steel, and then is the equivalent of having a 0.5% carbon. So that was, okay, let's say we put a 1.1% silicon, 1.1% silicon in my steel, and 1.1 divided 11 is 0.1. So if my steel was 0.2, now it behaves as if it was a 0.3 carbon steel. Now, let's say the steel has 0.8% manganese, right? And so if in addition of 1.1 silicon and 0.8% manganese, I have 0.8 manganese, I would have a steel that is equivalent of whatever carbon I have, let's say 0.2% for the sake of example, plus 0.1% because of the silicon, that is 0.3, plus 0.1% because of the manganese, that is 0.4. So this steel that has some amount of silicon and this amount of manganese, from the point of view of welding, behaves as a 0.4 carbon steel. It's not exact, it's not fundamental, but it's so useful and so practical. When you saw what Yoka uses to calculate hardness, they also use carbon equivalent. And nobody's fully in agreement about what the best carbon equivalent is. So some places settle on a calculation of carbon equivalent. They say, we calculate it this way, and I don't care about your science, right? So Eureka, they use 3 different carbon equivalents. If you read Alejandro's paper, you're gonna see that there are lots of researchers, each one with their own idea of carbon equivalent. Most people use something called the IIW carbon equivalent, just because they all agree on something that without being perfect is so useful. And it's this one that I'm showing you here. And there are relationships between the hardness and cooling rate. And they are embodied in the standards. Through Eureka, we're showing you something that is not the very best, but is simple enough to explain it in this class and to expect you to use it. There are more complex and better ones, and there are even worse ones. So we have this formula here that says, well, if you have this formula, you can make a prediction of hardness. We will not be using this formula here, but I want you to know that it exists. We use Eureka, that is so much better, and we can use it for model things. This understanding of relationship between alloying elements and cooling rate and predicting a hardness from there is central to the codes and standards in welding of structural steel, like D11 and the Canadian equivalent. Okay, you already know this. Briefly, other effects of time I want to discuss. One of the effects of time is coarsening, right? So if you hold it for too long or the temperature is too high, over time the austenite can coarsen. And that is a problem. For example, in some steels, you might end up with huge grains that end up being very hardenable. Another effect of time is you can dissolve precipitates. And if you dissolve the precipitates keep the grain size from growing. And if you dissolve them, then the austenite grains can move and grow too. Okay. Sometimes in time you can cause precipitates. For example, in stainless steels, you want them to be austenitic, but if they are hot for too long, for example, because you preheated a stainless steel or you use too high of a heat input, it might precipitate chromium carbides. And the chromium, if it is in a carbide, will not help your steel be stainless, and you ruin the stainless properties, and you ruin the toughness too. Here we have a curve, and I will stop on this slide, but I'll tell you what it is. And this is the topic of Alejandro's PhD studies. And it says, remember when we talked about cooling rate, CCT, continuous cooling transformations. But during heating, you also have transformations. You start at some microstructures that have ferrite and carbides, and when you heat up, you have to be in austenite. Most of the time, nobody cares. But there's some alloys and some processes in which things matter. Pipeline steels are ones that show that it might matter how fast we heat them, because the temperature at which austenite transforms can be different. We're going to see that this matters when we make calculations of heat affected zone. Also, in new processes like laser cladding or laser welding or laser heat treatment, the heating is so fast that the austenization doesn't happen as usual. It happens at very different temperatures. And when it happens at very different temperatures, the cooling down might end up being very different and difficult to explain. So we're going to stop here. The topics for we're going to have quiz 2 on Tuesday. The topics for quiz 2 are up to this slide we discussed today. And I have already listed those in our e-class page. You can see what is going to be there. I made a note of your feedback that I also uploaded it, so the exam should be better than before. We are all learning, and we can stop here. And thank you very much for attending this. You learn a whole lot of metallurgy very quickly. On Tuesday, we'll discuss the heat affected zone. I'll see you then.